Scholars, Ms. Perez here with our new physics lesson for today. Today we are continuing our exploration on static electricity, and we are going to be talking about defining Coulomb's law. Okay, so for today, you should have the following tabs open: your classwork document, your Google Classroom. If we are using the Simplicity of Science website, you should have that up as well. And the materials that you should have are your notebook and a pen and pencil. I chose the image that's on the screen right now because I thought that it was relevant to today's class. Though what you see in that picture are actually charged particles that are being accelerated really fast. And scientists have developed a technology to be able to take pictures of these. So this is a picture of actual tiny little subatomic particles that are moving around in a field that causes them to go around in spirals. I personally, if you're not one of my students, you wouldn't know this, but one of the reasons why I decided to study physics is because it makes me appreciate so much more the beauty in nature, and seeing pictures like these are like, it's dumbfounding. It's like, wow, like how can nature be so beautiful and intricate and detailed? And this is the kind of stuff that excites me, so I wanted to share that a little bit with you guys. Okay, so let's start our lesson. So we're gonna keep, so far in electrostatics and electricity unit, we have discussed how charged particles interact with each other. And we're going to try to make more sense of this from our perspective. Today, we are going to add a mathematical reasoning to these concepts while also learning about Coulomb's law. So consider this image that we have here of the student touching, that thing that he's touching is a charged ball called a Van de Graaff generator. So consider this image that we're seeing here. This shows there's static electricity. This person is touching a charged ball and their hair is going up. So today we are going to explore some more evidence and some readings that are going to help us consider the mathematical relationship between what we are seeing in this image and what we've discussed before in terms of static electricity. Our main guiding question for today is, how much force does a charge exert on another charge, and what do these forces depend on? So our agenda for today, we're going to do a quick do now, then we'll do some reading, we'll do a check for understanding, and then we'll do 2 practice problems, another quick check for understanding, we'll go over some key points, and then we'll complete our essay ticket. All right, so our do now. In your classwork document, you should answer this at the very beginning. It says here we have 3 diagrams. So there's the diagrams show 2 charged objects and the separation, so the distance between them. Rank the force that the left object exerts on the right from the strongest to the weakest force, and then explain how you made your ranking. So I just want to, before you start, I just want to name that we don't have all of the tools yet to be able to fully answer this question with like 100% confidence, but you will by the end of this lesson. So this is just to start getting our brain juices flowing so that we can delve deeper into this concept. All right, so take the next minute or to answer this question in your notebook, and when you are ready to come back, press play. You can press pause now. Okay, welcome back, scholars. So I am not going to go over the answer to this. We are going to go over this exact same question in a little later in this lesson. So let's move on. So Coulomb's law, what is this? So we're going to consider this question again. How much force does a charge exert on another charge, and what do these forces depend on? So I'm going to show you guys something on a simulation, and then we'll continue to explore this concept on our own. So here I have a PhET simulation. By the way, this is linked at the bottom of your classwork document if you want to come back and play with this on your own. Okay, so here what we have are 2 charges that are represented by these circles, And down here, it allows me to show how much charge each one of these has. So I just moved it so that each one of these has 0 charge. And then here at the top, it shows the amount of force that this charge Q1 is exerted by Q2, and then vice versa over here. So I'm going to start, while I'm doing this demonstration, write down anything in your notebooks, any observations that you're seeing, anything that you find interesting, any conceptual things that you're that seem important to you. Okay, so the first thing I'm going to do is I'm going to make this charge. I have the ability to make it negative or positive, so I'm going to start with making this negative. So I made this charge negative here, and is represented by the color blue, and nothing's happened because, and we see here this force is still, this charge here has 0 charge, so there's nothing going on. So that's one clue that we should see is like, oh, just because one object is charged and doesn't mean that it's going to exert a force on something that's neutral. So now I'm going to make this charge positive. And now that I make it positive, I see actually that the forces are starting to increase. So the greater my charge, the greater the forces that I'm seeing here. And the forces are represented both by the numerical value here and then also by this vector. So here, take a moment to note for yourself, in what direction are these two vectors pointing? Right, so they're pointing towards each other. So that tells me, we discussed previously that a negative charge is attracted to a positive charge. And I see that here now with these two vector arrows that are pointing towards each other. Right, so that tells me that it's attractive. Now let's do, I'm going to make this charge negative. So now I see the negative, it starts to, because they're both negative, like, what's the main difference that we've noticed from the previous example? Right, yeah, you should have noted that the arrows are now pointing in opposite directions. And now we should, that is correct, because we talked about how negative charges are actually repulsive, right? So the forces would be separating them. All right, so now let's keep, I'm gonna put this to be, so now both of these charges have the same amount of charge. So what happens when I change the distance in between these two charges? So note the distance is measured from the center point. So here, so right now the distance between these two charges would be 1 centimeter to 3 centimeters. Right, so I'm going to increase this distance by 2 centimeters, and I can see as I'm scrolling, as I'm pushing it backwards, that the force is decreasing. Right, so the further away I bring it, the smaller the force becomes. And then conversely, we started here at 4, the closer I bring it, the larger the force becomes. Right, so that's another important observation that we'll talk about more later on. One more thing I wanted to point out here that some of you might have noticed, that the forces here are measured in newtons. So just like we measured forces in newtons when we were talking about masses and gravity, or pushes and pulls in our kinematics, in our forces unit back in unit 2, it's the same unit of newtons that will be used for forces here as well. Okay, so now that we went through that demonstration, let's come back to our PowerPoint so that we can continue on. All right, so you are going to take the next 10 minutes to read and annotate the short reading that's in your classroom document. Make sure to annotate for key concepts and any new definitions. In your reading, you'll see that it refers to Coulomb, the man that actually who made the observations and then discovered this relationship between charges, and then eventually the law was named after him. So this is Coulomb, the French physicist. All right, so press pause now to so you can start your reading, and when you're ready to come back, press play. Press pause now. All right, welcome back, scholars. Let us continue on. So, wrapping up, well, not wrapping up, but summarizing. Coulomb's law, make sure, scholars, that you write this in your notebooks. I know it's in your reading, but this is a really important idea and concept that you should have in your notebooks. So take a minute to write this down. So Coulomb's law tells us that the force that two charges exert on each other are given by the following relationship, where the force here is equal to, what's important are the charges, the two charges, and the distance between them, and then squared. So that's called an inverse square relationship. And then K is a constant called Coulomb's constant. We won't really discuss exactly what that is. Just know that there are constants in nature that just exist, and this value K is one of them. It's just like a number that exists in nature that helps us understand more fundamentally the relationship between charges and the force between them. Okay, press pause if you need to finish writing this into your notes. Okay, so our first check for understanding, you should complete this in your classwork document. These 3 questions are laid out there underneath your reading, so you can press pause now to complete your classwork document, your check for understanding. This should take you around 3 minutes. Press pause now. Great, welcome back, scholars. So what happens when like charges are placed near each other? So you should have said that when like charges are near each other, they are attracting. Or no, sorry, like charges are repulsive. My bad, it's opposite. And then when opposite charges are placed near to each other, then they're attractive. Okay, and then what happens to a force of attraction if the charges are placed closer together? So from what so because of the mathematical relationship of one, like the distance between the charges is inverse, that means that the closer the charges are together, the larger the force. And we're going to see that in a minute in a video. Before we see the video, let's do these practice problems. So in the next 5 minutes, you will revise your do now and then solve the other practice problem that's your classwork document. So your do now is, so I just want to make sure we're all on the same page. So when we reach here to the practice problems, here you have your do now revised. So based on what we've discussed so far, would you want to change your response to the do now and then explain your thinking here and then solve the second problem? Okay, this should take you around 5 minutes or so. And press pause when you're ready to start and then hit play when you're ready to start back with the video. Press pause now. Okay, scholars, welcome back. We are going to explicitly go over the responses for the practice problems tomorrow in tomorrow's lesson. So if you're still feeling a little confused and might not be 100% sure how to solve this problem, don't worry. We are going to go into it in a lot more depth tomorrow. So the last check for understanding for today is this question here. If we have 2 charged objects that have a repulsive force of F. Think to yourself, if the 2 charges have a repulsive force, are they like charges or are they opposite charges? Right. They are like charges. So if the distance between these 2 charges is doubled, then what will the new force be? We don't have numbers to plug into all of these variables, but you do know we've done proportional problems like this before, where you plugged in 2 times the distance into here, right? So that should give you a clue into how to solve this problem. All right, so let's go through this question to make sure we're all on the same page. So if the distance between the two is doubled, then let's plug 2r here into our distance to see what happens. So my force is equal to kq1, q2 over, and now I'm going to do 2r instead, and this whole thing is squared. So if I solve this, I will have all my other variables remain there because I don't know what they are. They're just constants. But my 2 here gets squared. So then 2 squared is 4. So then I have 1/4 in front. So this here is my original force. And now I just see that by doubling the distance, the strength of the force actually becomes 1/4 of the original force. So the answer should have been A. Okay, if you have any questions about how we solved for this, take a note of it so you can ask your teacher later on. Okay, so now let's write down these really important key points into your notebooks. And please write these down as I'm reading them, as you're following along. So we saw that there is a direct relationship between the magnitude of the charge and the force it exerts on another charged object. Right? So the two charges are directly related to the force. And then there's an inverse squared relationship between the magnitude of the distance between the two charges and the force that they're exerted on each other. So like we saw in the previous problem, I mean, as the distance between was doubled, the force was actually 1/4 less. So there's this inverse square relationship. Right, press pause if you need to finish writing these into your notes. Oh, a really important point that I wanted to make here is that we made observations and we saw that these were well, and also we did some readings, and we saw that these are the relationships that govern the forces between two charges. Coulomb, the French physicist, he made some scientific discoveries and recognized that that's how charges affect each other, and then it was given the name Coulomb's law. So as physicists, it's really important to remember what the relationship between objects are and not so much like the name that something has, because the name just came later. Coulomb, and it was named after his honor. So it's more important to recognize how charges are related to each other as opposed to just memorizing like a Coulomb's law. All right, so our exit ticket for today, we are going to watch 30-second clip of Bill Nye, the science guy. And we are using the vocabulary you learned today, explain what happens to the second balloon when the first one changes position. Right, so you can see here already that Bill Nye has a balloon in his hand, and he's going to be moving it closer and further away from the balloon. So again, using today's vocab, explain to us in your classwork document what is happening here. Let's watch Bill Nye.
Oh, hi. Rub a balloon on your hair.
Actually, I'm going to keep him silent. So just watch what's happening. So you see there, as he brought the balloon closer to the balloon that's hanging, what did that balloon do? Okay. I'll also link this video in your classwork document if you want to watch the rest of it. All right, so wrapping up for the remaining of the time in class, make sure you finish up all the sections in your classwork document and that you submit everything into your Google Classroom tomorrow. I mean, before the end of the day. tomorrow we are going to continue our exploration of Coulomb's law, and hopefully a lot of the questions that came up today will be answered tomorrow. I hope you have a wonderful day. Take care.